ओके अस्सलाम वालेकुम। स्क्रीन शेयर्ड है आपके पास?
Yes, sir.
So I'll first point something out in the previous lecture. So if you see, I have uploaded the slides with solutions, and this one thing is important because the the way this answer is expressed in the book is not technically correct. Okay, so he says what he want. I mean, you know what he wants to say, but you need to be precise. So in this example, you have W as the input, and although it's on the y-axis, but it's still the input because it's the load that is the input, and X, the deflection, is the output. Okay, and that's why the question is obtain the deflection of the system model as a function of W. So your task is to express X as some function, yeah, of W. So you can imagine this plot like X on the y-axis and W on the x-axis, and that is what you want to do. So if you follow all the reasoning given the example, this is okay, because here you want to express W as a function of X from the Hooke's law and all the other combinations, but then you have to invert this relationship. Okay, and you have to, when you solve this for X, then you can't. So these conditions are okay here because X is the independent variable. But if you write here X is less than D and X is greater than or equal to D, this will be wrong because that X is your output. तो वो output तो आपने calculate करना है. So the conditions must be expressed in terms of the input, and that input is W. This is something which should also be clear to you from signals and systems. ठीक है? Signal system के perspective से आप इसको देखें, so you have a system with W as the input and X is the output. So if you want to express X in terms of W, these conditions must be given for W, not for X. So आगे दो तीन और एग्जांपल में भी इसने गलत किया है. We will have to fix these things. Okay. So let's get to the today's lecture. And the purpose here is to actually decide when do we take the geometry of an object serious and how important role it plays in the equations of motion. Similarly, the free length of a spring, yeah. So L here represents the free length of a spring which has not been stretched or compressed. Similarly, this dimension A here informs you about the center of mass. Center of mass G के बारे में A बता रहे कि ये इस point से कितना आगे. And E is just the name given to a point which will represent the equilibrium position. So E is the equilibrium position. So अब यहाँ पे जब ये move नहीं कर रहा, तो then E and G they coincide as far as x-axis is concerned. But when you stretch, or when the body moves to the right, the rigid body, the spring is actually stretched, and then although G moves forward, but E doesn't move because E is the reference. So E only tells you that you are measuring the deflection of the spring from the equilibrium, okay, and not from this point. Okay, if you measure it from this point, then it will be L plus A plus X. This X has to be added to A and L, and that will be your displacement. We want displacement of the spring only. Okay, so that's why E provides us with a fixed coordinate system. You have a fixed coordinate origin. Of course, this is also a fixed coordinate origin, but we don't want to use that. We want to use this as a fixed coordinate origin. Okay, whenever you see this shaded region, okay, this shaded region, and you also have the shaded region. So this shaded region, by convention in schematic diagrams, will either represent a rigid support. For example, this is a rigid support, rigid support, rigid support, or the same symbol will also represent the fixed coordinate origin. So if you now look at this, if you move from A to B, of course, the rigid body has been relocated, and that resulted in the extension of the spring. But as far as the equations of motion are concerned, you only need a free body diagram for the rigid body. Rigid body यहाँ पे ये है, ठीक है ना? अब once you have the rigid body, you only need to list the forces, and there is only one force, one unbalanced force, and that is the force from the spring. And why is this force towards the left? Yeah, because the spring has been stretched towards the right. You see, so this arrow is rightward, this arrow is leftward, and that minus sign is automatically taken care of by this left arrow, and that's why you don't need the minus sign here. But this kx is the only unbalanced force acting on the rigid body. Now, so it's a two-step process. When you observe this relocation, then you represented that by a free body diagram, and now although you have the same shape like cube or rectangle with some center, but this shape now does not matter, because this is just a rigid body, and the dimension A was only important when you wanted to locate E. कि ये E जो जिस जगह से आप X मेजर कर रहे हैं, फॉर एग्जांपल आप घर से, ये आपका घर है, ठीक है, और यहाँ से आप सुबह स्टार्ट करते हैं, so you decide that okay, you will measure everything from your home, तो ठीक है, लेकिन but if, and let's call that E, but if someone asks you where is E located with respect to some other reference, let's say ये आपका सिटी सेंटर है या कोई और जगह है, तो ये आपको उधर हेल्प करेंगे ये दो वेरिएबल्स E और L, A और L. So other than that, if you are happy with X, then you don't need this information. So which means that A and L, they will be disregarded, and that's why this shape doesn't matter. You just model this as a point mass. You just model this as a point mass, okay? And spring is as it is. So there is no difference between this diagram and that diagram, and that brings us to real versus ideal spring elements, okay? So there are two things which you need to remember whenever you see these diagrams. You need to distinguish between real spring, and real spring is much more complicated. It has mass as well, it has stiffness, it may have other chemical properties, physical properties. But when you say ideal spring element, this ideal spring element has only one property, and that is K, okay? It has no mass, it has no charge, it has no actually I mean, you can imagine any optical properties, any chemical properties, nothing. So and one other thing is that the dimensions or geometrical shape of this mass doesn't matter, because you can think of this center of mass as a point particle, okay? So we assume point mass. And this I already explained. Rigid body support and fixed coordinate origin, they are both represented in the same manner in these schematic diagrams. So what you learn now is that if equations of motion is all you need, then you can disregard these details, and you can always represent a rigid body by a point mass in these diagrams. But there is one more complication, and that is the effect of gravity. Let's say the same arrangement is inclined or it's vertical. Maybe it can be like that as well. Okay. In both cases, you have the effect of gravity. Now, what gravity does is now important, because this L and this A, they never appeared into this diagram, okay? And if, for example, if I now want to write the equation here, they won't appear. So I'll just write second law, that is, second law is always written for rigid body. So if it's mx double dot, and the only unbalanced force here is kx, although in the diagram the arrow was helping me because these arrows are opposite, so I don't need to care about the minus sign. But when I'm writing an equation, the equation needs a reference, and here the reference is, let's say, x double dot. So this kx I know is opposing that, so it will be minus. Okay. So if this is plus, this has to be minus. Uh, because this force is opposing x dot. And you see that in this equation you don't see any L, any A, nothing. But here, because of gravity, you will see some one term. Because of the if you take this vertical force, and if you take this component, that component is of course mg sine of phi, and that mg sine of phi is a force, unbalanced force. So even if this body doesn't move, it will still uh, of course, if you don't have any other force, this component of the weight will have some initial displacement, okay, and that displacement is what you call the static spring deflection. Why is it called static? Because it is possible that this x is 0. Let's say it stops there. You imagine some scenario where it stops there. So when it stops there, this static deflection will still be there. Now that static deflection will give you, so what you can do is that if you have this mass m, and let's say this x is 0, no further displacement, but this initial displacement delta st, the restoring force because of that will be k times delta st, and this was a result of this force, which is mg sine of phi. So because we have equilibrium, static equilibrium, yeah, these two must equal, and that's why you have this equation that k times delta st, which is the restoring force, is must equal in magnitude to the force which was causing it. Now what is the consequence of this? The consequence of this is that if you now want to write the equation for this free body, this free body has one force which is mg sine phi, and the restoring force will include the force as a consequence of x as well as the force as a consequence of delta. We don't need to take into account L and A because they are free lengths, and free length will not give rise to any force. So which means that if I now want to write the equation of motion for the rigid body, it will be m times x double dot as usual, and here I will write the unbalanced force. The unbalanced force will be mg sine of phi, yeah, in the direction of x, so it is plus, minus the restoring force. So that is k times x is the additional displacement, and delta st is the static deflection, the deflection, which was purely because of gravity. So now you can see is that this mg sine of phi will cancel out with this k times delta st. Yeah, that's why we call it static deflection. So you see that even from this equation, even the effect of gravity can be eliminated. At the end, you get an equation which is no different from this equation, you see. So there is no difference between this one, and even this one, because the effect of gravity has been incorporated into a change of reference. Yeah. So you choose the equilibrium as your reference, yeah, and then you don't need anything. So that's why if you measure everything from that equilibrium, then you are fine. Then the effect of gravity will cancel out on both sides. Okay. Do you have any question regarding this topic? Because you will have to use this in many examples to come. So let's begin. So our first example today is 4.2.1, and here you he starts with the fact that the moment of inertia I of an object And usually when you say that, you mean the inertia, moment of inertia about its own center of mass, can be calculated by measuring its oscillation frequency. Now, this is not something new for you. We have um, solved a few examples in which the frequency of oscillation of simple harmonic motion allowed us to calculate the moment of inertia. That is something we already know. So we will need something similar, and for that purpose you have a connecting rod. This is your connecting rod. It connects to shafts or to objects. It has a mass of 3.6 kilograms. So इसका mass given है यहाँ पे 3.6 kilogram. Oscillates with a frequency of 40 cycles per minute. So the natural frequency you see is 40 cycles per minute, and usually it's a good idea to convert it to cycles per second. That means that you divide this by uh, 60, okay? Because 1 minute is 60 seconds, so this should give you two-thirds cycles per second. And when it is supported, now this frequency of oscillation is observed when it is supported from on a knife edge. ये knife edge आपको यहाँ पे छोटा सा नजर आ रहा होगा. That is your point O. And its mass center G, this G, is located 0.15 meter below the support. तो ये O और G के दरमियान जो distance है D, that D is basically 0.15 meters. Now calculate the moment of inertia about the mass center. So you are required to find I about G. Okay. Now we're not given any other information. We want to even if we can calculate Ig, otherwise we want to calculate it from the frequency. Now उसके लिए जरूरी है कि हम इसके लिए equation of motion लिख दें. So it's a good idea to model this as a pendulum. Yeah? So if you assume that a pendulum of rod length d, this is massless by assumption, and all the mass is concentrated. Actually, no, the rod is not massless. The rod is 3.6 kilograms. Okay, so you have a rod which has a mass of 3.6 kilograms. So this is point G, this is point O, and you know, so there is no concentrated mass here. Okay, this is distributed mass, and you know how to write moment equation for that. Okay, moment equation about point O. Okay, rotation O के about होगी ना. Okay, let's call this theta. So when this is theta, you will write I. The moment of inertia will not be about G, it will be about O. Remember, this is G, this is O, and when we write equation of motion for the pendulum, we take it about that pivot O, because support वहाँ पे knife edge पे है. Knife edge आपका O है, G नहीं है. So I O times theta double dot is, because it's a moment equation, so here you need to write the unbalanced moment. Okay, unbalanced. जिस तरह हम अनबैलेंस फोर्स कहते हैं, हम यहाँ पे अनबैलेंस मोमेंट कहेंगे. अनबैलेंस मोमेंट यहाँ पे क्या है? द सोर्स इज mg वेट, और mg का कौन सा कंपोनेंट जो कि परपेंडिकुलर है टू द रॉड. दैट टर्न्स आउट टू बी साइन ऑफ थीटा. You can verify that yourself. And this is force, but we need moment, so the moment here is d. Yeah, it's d. Actually, this depiction is correct, d, but this is incorrect क्योंकि length d नहीं है, ये आपका d है. ठीक. एंड दिस इज नॉट नेसेसरली इन द सेंटर, ये भी बता दूं आपको, ये अगर सेंटर होता तो फिर ये टोटल लेंथ 2d होती। इसने इसके बारे में कुछ नहीं कहा कि ये क्या है, ठीक है। सो यू जस्ट नीड टू नो the distance between O and G, and that's all. Because all the mass is concentrated at G when you are writing the equation, so here you will write D, you will not write D by 2 or anything else. Okay, so now how does this lead to IG? We need IG, okay, but there is a hope that if we know IO, from IO we can get to IG. So let's work IO here. Uh, if I divide both the equations, both the sides by IO, what do I get? I get rid of this, yeah. And if I assume that theta is small, then sine of theta will be theta, and I have mgd over I naught theta. You do need a minus sign क्योंकि थीटा काउंटर क्लॉकवाइज है और ये जो फोर्स है क्लॉकवाइज है, so you have that minus sign. Now if this just sounds familiar, okay, whenever you see the double derivative, yeah, double derivative and then minus sign and some constant and then that quantity which has been differentiated, this reminds you of simple harmonic motion. Simple harmonic motion आपने डिटेक्ट कर लिया तो जो कांस्टेंट है that constant must be equal to omega n squared. So एक बात तो clear हो गई कि now we have omega n squared. Now omega n squared, but our purpose is to write an expression for IO, and IO from this will be mgd divided by omega n squared. Okay, so far we are safe. Let me just write this down. I naught is equals mgd omega n squared. So let me just write it down. What we have done so far is IO is mgd divided by omega n squared. Now the question is, m is given, g is 9.8, d is given, okay, so ये तो clear हो गया. अब omega n कहाँ से आएगा? Omega n यहाँ से आएगा क्योंकि that 40 divided by 60 cycles per second is the frequency in cycles. So if I multiply this by 2 pi, and if I multiply this by 2 pi, so I'll get 2/3, and 2 times 2 is 4 pi over 3, and this will be radians per second now. And that is your omega n, okay? So इसका मतलब है कि मुझे omega n भी पता चल गया. Now I know everything. I know m, I know g, I know d, I know omega n, and I take the square. So I will get my I naught, or IO, sorry, if I call this IO. Now my actual purpose is to find I about the mass center, which is G. So IG or IO के दरमियान क्या relationship है? For that, we use the familiar parallel axis theorem, which you know that you have used that many times, that I about a point which is away from the center of mass is simply I about the center of mass plus the total mass of the objects and the distance between G and O, and that is D in this case. So IG, the unknown, is simply IO minus MD squared. क्योंकि आपको I नॉट IO आपने यहाँ से कैलकुलेट किया, M और D आपको पता है. So this is how you calculate the inertia about the mass center. Are there any questions in this? इसमें the most difficult part in this question was the realization that this can be modeled as a simple pendulum. ठीक है, उसके बाद तो फार्मूलाज हैं, आप सारी चीजें याद आ जाती हैं. Okay, the next example is very easy, but things can be complicated in exam or in assignments. because I do expect you to come up with this model. For example, यहाँ पे इसने बताया हुआ है कि you have a beam, okay, and a beam is supported from the sides. So um, simply supported beam है, लेकिन ये कौन सा वाला है? ये vertical वाला नहीं है, ठीक है ना? ये वाला vertical वाला supported नहीं है, side वाला है. So and cantilever भी नहीं है क्योंकि एक side पे free नहीं है. So the vertical motion of the mass m attached to the beam. So ये beam के ऊपर एक mass आपने रखा हुआ है जिसको support कर रहा है. It can be modeled as a mass supported by a spring. अब देखो ना, अब ये जो sentence है ना, ये मैं चाहूँ तो मैं निकाल सकता हूँ क्योंकि I expect you know that the beam is a flexible body and you know that a flexible body can be modeled as a spring. हाँ, ये आपको imagination ये करनी पड़ेगी क्योंकि ये ideal spring है. आइडियल स्प्रिंग का मास नहीं होता और बीम का मास होता है, तो बीम का मास आप फिर इस m में ऐड करेंगे, m प्लस समथिंग, ठीक है. सिंप्लिसिटी के लिए यहाँ पे इसने दिया हुआ है कि assume the beam mass is negligible compared to m. ये तो प्रैक्टिस एग्जांपल्स का मतलब ये होता है कि he has done all that assumption for you, but I do expect you to make this assumption yourself. अगर मैं ये हटा दूँ ये चीजें, so you are expected to include the mass of this beam with the mass of the rigid body and model that as an ideal spring, okay, so that the beam can be modeled as an ideal spring. Okay. Now determine the system's natural frequency of oscillation. अब यहाँ से natural frequency of oscillation पिछले example, the previous example must guide us, okay. Okay, if we can write down the equations of motion and if we can identify simple harmonic motion, now I'm telling you the strategy that if you write the equations of motion and if those equations of motion point towards simple harmonic motion, that simple harmonic motion will give you omega n squared. Okay, that is the strategy now. So मॉडल उसने बनाया हुआ है और हमने क्या करना है कि whenever you see such a diagram, you need a free body diagram. फ्री बॉडी डायग्राम यहाँ पे किस चीज का बनेगा? m का, क्योंकि फ्लेक्सिक रिजिड बॉडी का बनता है. So you have this mass m और you want this to move downward और स्प्रिंग इसका वर्टिकल डायरेक्शन में बनेगा क्योंकि डिफ्लेक्शन वर्टिकल डायरेक्शन में है, लोड भी वर्टिकल डायरेक्शन में है. सो वन थिंग इज दैट इट हैज ए one external force is mg, its own weight, and the restoring force from the spring will be opposing, क्योंकि जब आप इसको कंप्रेस करते हैं so this will oppose in the form of a restoring force that is opposing it. So that will be k times x. You don't need the minus sign, but we will now need the minus sign here, that if I want to write Newton law for the rigid body, it will be m times x double dot, and the two forces, the two unbalanced forces, one is mg and one is minus k times x. अब इसमें एक चीज हमने मिस कर दी है. कौन सी चीज हमने मिस कर दी है? हमने मिस की है ग्रेविटी का वो इफेक्ट जो स्टैटिक डिफ्लेक्शन होता है. क्या स्टैटिक डिफ्लेक्शन? ये x जीरो भी हो जाए ना वो फिर भी रहता है. इसका मतलब ये है कि ये फोर्स कंप्लीट नहीं है. This will be kx plus that static deflection delta. We call it delta for simplicity. This delta will be a consequence of this mg even if this x was zero. So हमने include करना है kx plus delta, but we know this mg will cancel out with this k times delta, so that will disappear anyway. So which means that we can write down mx dot equals minus kx, divide both sides by m, so x double dot equals minus k over mx, and now this is perfectly in simple harmonic motion form, and omega n squared now is k over m. Yeah, minus sign is part of the definition, so omega n is simply k over m square rooted. Okay, and so this is natural frequency. Because you will be writing units here, when you write radians per second, that should be the answer should be good enough. But if someone insists to have only one interpretation of this natural frequency and that is cycles per second, तो फिर आप चाहें तो आप इसको 2 pi से divide कर सकते हैं. But that I mean, normally when you want to specify this, you say, okay, angular frequency or cyclic frequency. यहाँ पे उस तरह का नहीं है. Natural frequency can be reported in the form of radian per second or cycles per second, and they are both equally good enough. So, but you need to remember there are two ways. When you write this mg, you must not forget to write delta. अगर आपने ये complication से बच जाना है तो आप gravity का effect उधर ही cancel कर दें और equation लिखी ना सिरे से, ठीक है? Now the next example is again a spring mass system, but this time it's a torsional system. Okay, so you have a torsional system like the one shown on the right. You have a cylinder, okay, having inertia A, uska inertia given है, is attached to a rod whose torsional spring constant is kT. अच्छा, अब यहाँ पे ये क्वेश्चन बहुत आसान है. क्यों? एक तो इसने यहाँ पे बता दिया टॉर्जनल सिस्टम, दूसरा उसने टॉर्जनल स्प्रिंग कांस्टेंट दिया हुआ है और इसने यहाँ पे बात की है इनर्शिया आई की, मास की बात नहीं की है. तो ये तो बहुत आसानी से आपको ये गाइड करेगा कि यू हैव टू मॉडल दिस एज ए टॉर्जनल स्प्रिंग. बट आई एक्सपेक्ट मोर फ्रॉम यू. ओके, I expect you that even if this is not given, even if this is not clear, even if this is not clear, and even if this is not clear, मैं सिर्फ ये बताऊं कि यहाँ पे एक cylindrical rod है, ठीक है? Now let's say I have a rod, and then I have a cylindrical body, और यहाँ पे एक support है, ठीक है? ये support है. अब यहाँ पे मुझे कैसे पता चलेगा कि इसको मैंने मॉडल करना है as a torsional spring and not as a linear spring? That will depend on the loading. इसकी लोडिंग अगर ट्विस्ट यहाँ पे इसके साथ, फॉर एग्जांपल if there is a pulley or a belt or some motor, so then I will know that this support will resist that twist, and here you apply something, there is the reaction, and this rod will be under a twisting force, okay, or a twisting action. So वो फिर आपने खुद डिसाइड करना है. ये भी हो सकता है कि दोनों, it is under an axial load as well as a twisting. तो फिर आप यहाँ पे उसको दोनों मॉडल बनाने पड़ेगा. आपको ये वाला मॉडल भी बनाना पड़ेगा और ये स्प्रिंग वाला भी बनाना पड़ेगा, ठीक है? That is something you need to be aware of. Now the angle theta is the twist. So assume that the inertia of the rod is negligible compared to inertia I. Again, यहाँ पे आप अगर ये information missing go, then you have to include that inertia as part of this inertia, so that the rod can be modeled as an ideal torsional spring. You know that. Now obtain the equation of motion in terms of theta and determine the natural frequency. वही दो questions. Equations of motion आप लिखेंगे, वहाँ पे simple harmonic motion आपको मिलेगा, तो उधर से आप natural frequency omega n recover कर सकते हैं. So modeling part ये हो गया कि you model the rod as a torsional spring for obvious reasons, क्योंकि यहाँ पे given है, और support चूंकि इधर है, so now you can have your free body diagram. Free body diagram में आपको पता है the only unbalanced moment is caused by the torsional spring, and that is kt times theta, ठीक है? और माइनस साइन की इसलिए जरूरत नहीं है कि थीटा को अपोज कर रहा है, अपोज करना चाहिए उसको. That's what you mean by restoring torque. So I can now write the moment equation, और यहाँ पे ऑल इसने टेढ़ा शो किया हुआ है लेकिन कोई ग्रेविटी का इफेक्ट नहीं है. अगर इफेक्ट है भी तो हम कह दें कि वो कैंसिल हो जाएगा. सो वी कैन नाउ राइट द मोमेंट इक्वेशन about the axis. So if it's about the axis, then I is also about the axis. So I times theta double dot will give me kt times theta, because this is the only opposing, minus sign moment. So if I now divide both sides by I, the inertia, it will be kt time divided by I with the minus sign and theta. So this is very easily written as a simple harmonic motion. So omega n squared is kt over I, and omega n is that quantity square rooted. और अगर आपको fn चाहिए तो आप उसको 2 पाई पे डिवाइड भी कर सकते हैं बाद में, ठीक है। कैलकुलेशन आप बाद में खुद कीजिएगा, यहाँ पे वैल्यूज वैसी भी नहीं गिवन, ठीक है। सो इन दिस क्वेश्चन यू आर ओनली expected to write the expressions. Okay, the next one is something which you have seen over and over. Yeah, inclined plane, a rolling wheel, and you see this assumption more and more, okay, without slipping. The only thing which is new in this case is the spring. So of course you are given, you want to determine the equation of motion of the cylinder in terms of the coordinate x. So ये ज़हन में रहे कि our equation should be in terms of x, x dot, x double dot, and so on. So we need to express this omega in terms of x, because otherwise we won't be able to write everything in terms of x. And that is why this roll without slipping will help us, because this assumption means that this translational motion and the rotation omega, remember, don't confuse it with this alpha you fixed it. This omega and this x dot are related with the radius r, okay? And that means that whenever we see omega, that will be replaced with x dot by r, okay? So one more thing is that we can, before we can write the equations of motion, we must have a free body diagram. Free body diagram में आपको gravity को आपने basically decompose कर दिया, तो one component is along the incline and one is perpendicular to the incline. mg cos alpha will be balanced by the normal force. So normal force must equal mg cos alpha. These are the magnitudes. Arrows वैसे cancel कर रहे हैं. ओके, ये तो क्लियर हो गया, क्योंकि जंपिंग नहीं है इस डायरेक्शन में, कोई जंपिंग बाउंसिंग नहीं है. नाउ एज फार एज द इंक्लाइंड, द मोशन अलोंग द इंक्लाइंड इज कंसर्न्ड, वहां पे हमें पता है कि वी हैव द कंपोनेंट अलोंग द इंक्लाइंड ऑफ द ग्रेविटी, and that will give us k times delta, okay, the restoring force opposing that. And if it moves in addition to that, you will have kx as the restoring force against x as well. So we can easily now write down the equation of motion for the rigid body, which is m times x double dot, and that is the unbalanced force will be mg sine of alpha with a plus sign because it is in line with x, they're both having the same direction. और जो restoring force है spring का, उसमें x का contribution है और जो static deflection है उसका भी है. So दोनों ऐड कर लेते हैं, and because both are opposing x, so it will be with a minus sign. But the good news is that mg sine of alpha and k times delta can be cancelled out, and you are left with. But one more thing, sorry, there is one more thing. This friction force is also unbalanced. Okay, so you have to write down minus ft as well. T is the tangential force at this point of contact. So our final equation of motion will be mx double dot equals minus kx minus ft. Okay. Now here a common mistake which students can make is to somehow recall examples from physics, and whenever you see this friction force, because you know it's friction force, it's opposing, yeah, this motion, and you also know the normal force का expression भी आपको given है, so you are tempted to write this mu times n. अब ये लिख देते हैं, फिर आप यहाँ पे plug कर देंगे, ठीक है ना, but that will be wrong, obviously wrong. क्यों? ये क्यों गलत हो जाएगा? किसी को याद आ रहा है ये? I am giving you a hint that this assumption rolls without slipping means more than just writing this down. Okay, सिर्फ ये नहीं है, इसका एक और मतलब भी है कि ये जो friction force है, this is, क्योंकि ये इसकी maximum value है, ये इस force की क्या है? Maximum value है. मैक्सिमम वैल्यू को क्रॉस करेगा तो ये स्लिपिंग शुरू होगी, स्लिपिंग तो अभी हो ही नहीं रही। नो स्लिपिंग का मतलब ये है कि आपका जो एफ टी है फ्रिक्शनल फोर्स दैट इज लेस देन द मैक्सिमम। तो अब इस इनइक्वालिटी का तो आपको कोई फायदा ना हुआ ना, लेस देन है तो सो व्हाट, you cannot use this inequality for calculating the value of ft। इसका मतलब ये है कि ये आपके लिए यूजलेस हो गया। आप इस तरह करेंगे कि you will now have to write the moment equation, और कोई हल नहीं बचा। मोमेंट इक्वेशन आप लिखेंगे, you can either write it about g center or you can write it about p। It's easy to write it about g। advantage g का ये है कि when you choose g as your point of about which you write the moment equation, तो ये जितने भी forces है, ये वाला, ये वाला, ये वाला और ये n वाला, इन सब के moment zero हो जाएंगे। they will all give zero moment क्योंकि they all have their line of action intersecting this g। So the only force left will be ft, and that ft will have a moment given by ft times r, ft times r, okay? Now ft times r will give you a moment which is clockwise, okay? Now we need to write down whether this is plus or minus. That will be dictated by omega. So on the left hand side we write I times omega dot, and I is about g, of course. Now if you look at I, don't assume things from your own side, just look at I। I का जो डायरेक्शन डायग्राम में शो हुआ है वो भी क्लॉकवाइज है। तो इसका मतलब ये है कि ये क्लॉकवाइज हर दफा नेगेटिव नहीं होगा, इस क्वेश्चन में ये पॉजिटिव हो जाएगा, क्योंकि ऑल वी नीड टू नो, जिस तरह हमने ये देख लिया कि x डिसाइड करेगा कि ये माइनस है प्लस है, तो यहाँ पे ये ओमेगा डॉट डिसाइड करेगा कि ये एफ टी टाइम्स आर प्लस है या माइनस है। दिस विल बी प्लस बिकॉज इसका जो मोमेंट है और जो ओमेगा का सेंस है वो दोनों का सेम है। So now we have two equations, okay? We have this equation with plus minus t, sorry, with minus ft, and we have this equation with plus ft. If we get rid of this r, if we divide both sides by r, I will have I omega dot by r. Now I have plus ft and minus ft, so this gives me a hint to add these equations so that I get rid of this unknown quantity, and that will give me, the addition will give me mx double dot plus I over r omega dot on the left hand side, and on the right hand side I'll be only left with k minus kx because ft will cancel out with ft plus minus. One thing is still missing because omega needs to be replaced with x dot by r, so which means that omega is x dot over r, so omega dot will be x double dot over r, and if I now plug that, I will have m plus I over r squared times x double dot, that is minus x minus kx. I can now divide both sides by this, so my final equation will be, actually I didn't even need to write this, okay? N doesn't matter here because I have another method for that. So if I divide both sides by this m plus I over r squared, I am left with x double dot equals minus x, and what multiplies x is k in the numerator, and m plus I over r squared in the denominator, and this is my omega n squared, okay? K over m plus I over r squared. Of course, if you want to find an expression for I, you can look at the table, and I think it's half mr squared because it's a cylinder, so उसका half उसके साथ लगता है, point mass नहीं है। So yeah, that was it. We have, actually we don't even need to express it in this form because in this question all we need to do is to write the equation of motion। ये इस फॉर्म में ओमेगा एन स्क्वायर्ड के फॉर्म में लिखने की जरूरत तब होती अगर यहाँ पे नेचुरल फ्रीक्वेंसी भी जो है ना वो क्वेश्चन होता। So maybe we can just leave it and just ignore this, yeah, and we just write down this as your answer, x double dot इक्वल्स माइनस के ओवर एम प्लस आई ओवर आर स्क्वायर। एक्स ज्यादा से ज्यादा आप आई के लिए एक्सप्रेशन लिख देंगे हाफ एम आर स्क्वायर। समझ आ गई ये वाली? इसमें कोई क्वेश्चन है तो आप पूछ सकते हैं। ओके, the next example is, it looks complicated but it's easy. The only thing you need to remember is that the pulley is not a simple pulley. Normally जो पुली होती है वो सिर्फ ट्रांसमिशन का काम करती है, ठीक है। तो यहाँ से यहाँ पे फोर्स ट्रांसमिट करती है, तो एक ही पुली होती है। यहाँ पे ये पुली एक नहीं है, इट्स ए स्टेप पुली। स्टेप पुली का मतलब ये है कि यहाँ पे बेसिकली दो व्हील्स हैं, दो दो पुलीज हैं, एक का रेडियस r1 है, दूसरी का r2 है, और spring connected to the first one and the mass and this string is connected to the other one. Okay, so इसका मतलब है कि इसके दरमियान जो ये फोर्स ट्रांसमिट करेगा ये इतना सिंपल नहीं होगा. We need to do something. Assume small motions and assume small motion का मतलब ये है कि theta can be assumed to be small. The pulley mass is small compared to the mass m. Values are 1, r2 given a, mass given a, k given a, computed the natural frequency of the system. Okay. So natural frequency of the system, we need to write the equations of motion. But for that, first we need to establish the free body diagram. So m, इस पे ये force mg हो जाएगा, और यहाँ पे force एक. Let me just express two different forces. One force will be from the static deflection, which is m times, बल्कि वो static deflection वाली बात बाद में कर लेंगे, ठीक है, क्योंकि deflection x में आनी है, और ये अगर सिंपल पुली होती, ये r1 r2 का चक्कर ना होता, तो ये फोर्स और ये फोर्स सीधा इधर ट्रांसमिट हो जाता, ठीक है। तो फॉर एग्जांपल यहाँ पे अगर ये x है तो ये भी x होता, ठीक है, कि सेम पुली है। सो k टाइम्स x, यहाँ पे फोर्स होता इसका रिस्टोरिंग, और वही फोर्स यहाँ पे ट्रांसमिट होता, और यहाँ हम लिख सकते थे माइनस की जरूरत नहीं है, अपवर्ड एरो, वी विल सिंपली राइट k टाइम्स x, ओके। और ज्यादा से ज्यादा हम वो डेल्टा लिख देंगे m स्टैटिक डिफ्लेक्शन के लिए। लेकिन ये गलत है, इसलिए गलत है कि the pulleys are not transmitting the force in that simple manner because two different basically pulleys are involved. तो उसका हल ये है कि आसान तरीका ये है कि जब भी आपके पास डिफरेंट डायमीटर्स हो या रेडियाई हो तो आप मोमेंट लिया करें। जस्ट टेक द मोमेंट अबाउट द सेंटर। सो मोमेंट जब आप लेते हैं तो क्या होता है कि यू हैव लेट्स से यहाँ पे टेंशन है T, टेंशन T है, ठीक है। तो ये टेंशन T यहाँ पे, क्योंकि स्टैटिक बैलेंस mg के अगेंस्ट भी चाहिए, T अपवर्ड एस mg डाउनवर्ड को सपोज वो करेगा। सो दिस T का जो टॉर्क होगा अबाउट m, बिकॉज दिस T हैज टू बी हियर, इट हैज टू बी अपवर्ड, बट फॉर द पुली साइड इट हैज टू बी डाउनवर्ड। यहाँ पे किसी भी जगह आप फ्री बॉडी ले लें वो कैंसिल हो जाएगा। सो इसका मतलब ये है कि इफ आई वांट टू राइट द मोमेंट बैलेंस अबाउट दिस, तो इसका जो टॉर्क है वो दैट विल बी T टाइम्स R2, T टाइम्स R2, और जो स्प्रिंग का है वो है K टाइम्स X, and remember because it has to come downward, the spring will be stretched towards the left, so the restoring force will be towards the right. So Kx times R1 and T times R2, they will be opposing each other. Okay, so this moment and this moment they will oppose each other, which means that T अब यहाँ पे थोड़ा सा मैंने गड़बड़ ये कर दी कि वो जो ये K टाइम्स X नहीं होगा, ये K टाइम्स X प्लस डेल्टा होगा, क्योंकि वो स्टैटिक डिफ्लेक्शन में हो जाएगी। K टाइम X प्लस डेल्टा टाइम्स R1, yeah. So T equals K times X plus delta R1 divided by R2, और ये X भी ठीक नहीं है, even the X is wrong. Let's call this deflection, actually arrow, I need to fix the arrow because the deflection, if I do, the deflection will be towards the right, so this force will be towards the left, yeah, Ky, y plus delta, okay. So it's y plus delta. Or maybe we just get rid of this mg, okay? क्योंकि मुझे पता है कि cancel हो जाना है, so why should we complicate things? We simply remove that and we simply write that k times y, yeah, k times y. So k times y, और mg को मैंने खत्म कर दिया. But the question is how to relate x with y. तो उसके लिए हमें पता है कि when you have two different circles with different radii, and if you have motion along those different circles, the angle will still be the same. So the angle theta is not only x over r2, yeah, x over r2, it must also equal y over r1, yeah. And that means that we can now forget about theta and we can now write y in terms of x, which is r1 divided by r2. So here I can now have a final expression for t equals r1, yeah, k times r1 over r2 will be squared because it is coming here as well as here, and x will be here, okay? So that's the only unbalanced force because mg will be cancelled with that static deflection, and I can now write down the Newton's law for rigid body, which is mx double dot, and this k times r1 by r2 squared x, this will be with a minus sign because it's opposing. So if I now divide both sides by m, so this will be my omega n squared, k over m r1 over r2 squared, okay? So you see it, I mean, ignoring that effect of gravity made our life easier. एंड अब यहाँ पे आपने सिर्फ वैल्यूज प्लग करनी है, k की ये वैल्यू है, m की ये वैल्यू है, r की ये वैल्यू है और 1 की r2 की, एवरीथिंग इज इन प्लेस, एंड पे आपने सिर्फ स्क्वायर रूट लेना है बस. ठीक हो गया? Okay, the last thing which I need to, this is not an example, not a problem, you just need to keep one thing in mind, that normally when we have diagrams like that, we think of the force as an input and we don't care where this force comes from, and maybe x is our output. But sometimes there are mechanisms like cam drives that will allow you to convert rotation by a motor to translation, and if you can control that translation, then you can disregard the detail and you can think of that displacement as your input. क्योंकि स्प्रिंग को अगर डिस्प्लेसमेंट मिल रही है तो स्प्रिंग ने उसको अपोज करना है. फॉर एग्जांपल यहाँ पे अगर आप इस बॉडी के लिए फ्री बॉडी डायग्राम ड्रा करते हैं तो दिस इज योर फोर्स. यहाँ पे अगर स्प्रिंग की तो आप कर रहे हैं तो स्प्रिंग डजंट केयर कि स्प्रिंग को ये डिस्प्लेसमेंट कहाँ से मिली है और कैसे मिली है. दैट डिटेल्स कैन बी डिसरिगार्डेड, एंड एज फार एज दिस फ्री बॉडी डायग्राम इज कंसर्न, यहाँ से इस स्प्रिंग का तो आपको k2x हो जाएगा, लेकिन लेफ्ट साइड से जो स्प्रिंग है उसमें, because the spring has two ends, one moves with x, the other moves with y, and this y comes from somewhere which we don't care, so we can regard this as our input displacement. So that's why our inputs can be force as well as displacement, and so once we do that, the unbalanced force will be y minus x, because we assume, if we assume that y is greater than x, then this is the restoring force. If we assume that y is less than x, then you have to write x minus y, and then this will be the force, okay? So that is something which we will know in examples anyway. This might come as a surprise to some of you कि x को हम जो है ना इनपुट कैसे ले लेते हैं, या y को मैं इनपुट कैसे मान लूँ. ये तो फोर्स नहीं है, फोर्स तो यहाँ पे तो टॉर्क है या फोर्स है. तो this is something which you can relate to your circuit diagrams. If you remember, if you have some complicated circuit and sometimes you have this voltage source, like in voltage source, Why do you call it a voltage source? Although you know that it's also giving you current. So in fact, it's a power source. Or you can say an energy source. आप इसको voltage source इसलिए कह रहे हैं कि you can control V yourself and you leave I to the load. आप ये कह रहे हैं कि I को मैं कंट्रोल नहीं कर सकता, I लोड ने डिसाइड करना है, करंट मेरी मर्जी का होगा, ठीक है ना, साइनोसाइडल या स्टेप या जो भी है. लेकिन आप इसको फ्लिप कर सकते हैं. इन सम सर्किट्स यू हैव ए करंट सोर्स. अब करंट सोर्स का मतलब ये नहीं है कि वो वोल्टेज नहीं देगा, लेकिन उसका जो वोल्टेज होगा दैट विल बी डिक्टेटेड बाय द लोड and the current is dictated by the user or some other control mechanism. तो जिस तरह यहाँ पे करंट सोर्स हो सकता है, यहाँ पे हमारे पास डिस्प्लेसमेंट सोर्स भी हो सकता है. सिंपल रीजन ये है कि यहाँ पे हम फोर्स को कंट्रोल कर सकते हैं अपनी मर्जी से, और यहाँ पे वाई को हम किसी और मैकेनिज्म से कंट्रोल कर सकते हैं जिसका डिटेल हमारे, जिस तरह करंट सोर्स का डिटेल वी डोंट नीड टू नो कि करंट सोर्स कैसे हमें करंट दे रहा है, वी डोंट केयर. We just model some complicated power supply by some power supplies are modeled as current sources, some power supplies are modeled as voltage sources. So that was it for today. You can close this now.